Okay, so looks like it's time for us to get going for today. I think the only couple of things I have to mention before we get started is the second assignment is now open. I did that yesterday afternoon. So that assignment, or maybe Saturday, I don't remember. Anyway, the second assignment is open. It's all about the sound chapter that we're getting started with now. So you should be able to go ahead and get started on that. This week there's a problem set in the lab session. Monday's class has already had theirs, so now Thursday's group should show up on Thursday. Please bring a calculator. You won't be allowed to use your cell phone as a calculator, so make sure you have one. For my part, I don't care what kind of calculator you have. You can't attach it to the Wi-Fi. Like, I guess that would be my only restriction. You can't have a calculator that you can talk to your friends on. Other than that, graphing calculator's fine, whatever else is fine. But you do need a calculator, you can't use your cell phone. We have a couple of spares, but not very many spares. So any questions before we get started? Last day we talked more about sound waves. We talked specifically about standing sound waves in tubes. We established the boundary conditions. So there's a pressure node at an open end and a displacement antinode, because those molecules are free to move in and out. At a closed end, we have a pressure antinode, because those molecules get really squished together and then they spread out. We get a displacement node because the molecules can't move. So those were our boundary conditions. When we have just the right frequency, we can get standing waves in the tube. So yeah, just make sure everybody's got their mask pulled up, please. So that was everything we got to last time. And today we'll start right off with an example. So this is a pretty typical kind of example. An organ tube has successive harmonic frequencies. So that means there are standing sound waves in the tube. One of the frequencies that we'll observe that we can measure is 786. And the very next standing sound wave happens with a frequency of 1310. And there are no other frequencies in the middle. Okay, so that's what it means by saying they're successive. So those two are adjacent frequencies, not in the middle. We can assume the speed of sound in air is 343 meters per second. And our first question is find the fundamental frequency of the organ. It might be tempting to say that the fundamental frequency is 786 because that's the lowest one given. But you don't know that. You're not told that that's the lowest. So let's see if we can figure that out. So we're given that one frequency is 1310 hertz. The next lower frequency is 786 hertz. So those two frequencies are separated by 1310 minus 786 equals 524 hertz. So when you subtract those two, you see that the frequencies, whatever they are, they're all separated by 524. At this point, you probably have a couple of options for finding the fundamental. The way I like to do it is let's just count down. So the next lower frequency after 786 would be 786 subtract 524, 262 hertz. And so that would be our next lower frequency. If I subtracted 524 again, I would get negative 262. Is that a sensible answer? No, that doesn't make any sense. Frequency is not negative. Therefore, this is the lowest frequency. That tells us that our fundamental frequency, F1, is 262 hertz. And like I said, this is not the only way to do it. Some people like to do all kinds of divisions and figure out the end numbers. I think this method is really straightforward. So this will get to your answer without any ambiguity or confusion. Okay, part B, and it's very typical to have this as part of the question. Is the organ open at both ends, or is it open at one end and closed at some ends? Some people will jump in with the answer, oh, it must be this way because that's what organs are like. Well, the truth is, some organs are open at both ends and some are open at one and closed at the other. So you can get different types. So you gotta be careful not to jump to conclusions here. Let's figure out if it's open-open or open-closed. And we'll use a result that we came up with last class. if tubes are open at both ends, then delta F is equal to the fundamental frequency. So that's something we did last time. If a tube is open at both ends and a tube is open at one end and closed at the other, then the change in frequencies is twice the fundamental. So that's a condition that we know. We figured that out last time. So let's apply that to what we have here. In our example, F1 is 262, but delta F is 524. So here we see that delta F is double the fundamental. Therefore, our tube is open at one end and closed at the other. I don't know if any of you are feeling it, but it feels like 1,000,000 degrees in here, like my glasses are fogging up on me. People in the back, you are most welcome to open those windows if you're finding it sticky as well. Or if you need to step out and get a drink of cold water, like no hard feelings, especially with the masks, making it quite warm as well. Okay, everybody good with A and B? Yeah, okay. Sometimes there's like a plastic cover on the windows. That's magnetic. You just take it right off and just lay it on the floor if it's covered up. And then you just pull the window open by the handle, like pull it down and then open. Okay, what harmonic number corresponds to the frequency of 786? So if you're looking at old random examples, you might see the question, which harmonic is this? Like we talked about last time, I think that kind of question, which harmonic, is kind of ambiguous. So I'll ask the question, what's the harmonic number? So now we'll look at our frequencies. We'll remember that we've got a tube that's open at one end and closed at the other. When we're open at one and closed at the other, it tells us that our harmonic numbers are all odd numbers. Okay. So if we have tubes that are open at one end, closed at the other, our frequencies are n times F1, or Fn, equals n times V over 2L, 4L. And our n's are all the odd numbers. Okay, so there's our general description of waves in tubes that are open at one end, closed at the other. That tells us that 262 is the n equals 1 harmonic. 786 is the next higher, that's n equals 3. 1310 is next higher, that's n equals 5. Okay, so we can just number those because we know how the numbers go. So 786 is the n equals 3 harmonic. Still good? Last bit, find the length of the organ pipe. So now we're going to try and solve for L. Let's come to this equation. Fn equals n times V over 4L. So that's our equation. We can pick any frequency here because we know the frequency and the n values for each of them. So we know n, we know frequency. We know that V is 343, so we can solve for L. So L is equal to n times V over 4 times the frequency. I'm going to use the fundamental frequency just because it's fewer numbers to put in the calculator. So n equals 1, V is 343 meters per second, divided by 4 times the fundamental frequency of 262 hertz. Gives us a length of 0.328 meters per second. My goodness, meters. Mondays. Okay. Length is definitely measured in meters, not meters per second. Okay, any questions? Okay, let's go to a more biological example. And let's think of a tube that's open at one end and closed at the other. An example I can think about is our ear canal. So that's open at one end. That's the outside of the ear. And it's closed at the other end. That's where you have your eardrum. So we might ask, what kind of standing waves, which harmonics can we get in our ear canals, right? So that's kind of interesting. And then we could further think, well, what does it mean that we get standing waves? Does that have some sort of impact for us? So if we think of our tubes that are open at one end and closed at the other, we could draw the standing waves in the tube. So I'm going to draw pressure waves. At the opening where your ear meets the air, the pressure is going to be at normal equilibrium pressure because your ear is open to the outside. So we've got a node and pressure there. At the eardrum, you've got a closed end, that's a pressure antinode. So this would be your n equals 1. This would be the fundamental. If we want to define that frequency, F1 is equal to n, which is 1, times V over 2L. Okay. Let's apply 2 bits of biology here. An average eardrum is about 2.5 centimeters. I'm sure there's bits of variation in different humans, but an average one is 2.5 centimeters. That takes care of our L. Here, we have to be careful about V. You might be tempted to use 343 because that's what you use when there's no temperature given, but there kind of is a temperature given. This is inside your ear canal of a human being. The temperature would be 37 degrees Celsius. Okay, so that's kind of a sneaky way to put temperature in there. So let's calculate our V. V is going to be 331 meters per second times the square root of the temperature, which is 37 degrees Celsius, plus 273 divided by 273. Put that through the calculator, and the speed of sound in the air in your ear canal is 353 meters per second. Okay, so we've got to use that for our V. So now we can get our frequency. 1 times 353 divided by 2 times 0.025 would give us about 3,530 hertz. Yeah?
I thought that the frequency formula for an open closed.
Oh my goodness.
Yeah.
4L. Okay, sorry, good catch. I did do the calculation, right? So this is what you should get on your calculator. I just wrote down 2 instead of 4. Okay, if we stop and do a check, we said average humans hear between 20 hertz and 20,000 hertz. So this is in the audible range for most average humans. So that's going to be the first standing wave. Let's see what the next standing wave would be. If we wanted to draw it, we have to put in another node. It's going to look like this. This will be our n equals 3 harmonic. 2 ways to calculate it. You could say F3 equals 3 times V over 4L. Or you could say F3 equals 3 times F1. They'll both give you the same answer. And you should get 10,600 hertz. Okay, so when you play a tone of 10,600 hertz, you should see a standing wave in the ear canal. This one is still audible. Let's go one higher. Let's try out n equals 5. So n equals 5, a little harder to draw. Something like that. F5 will either be 5V over 4L or 5 times F1. And we should get 17,700 hertz. And I'm rounding here to 3 sig figs because why not? Any higher than this, if we went to n equals 7, we would get something higher than 20,000, and an average human wouldn't hear that. So we're going to stop with the n equals 5 mode. Here's something I think is kind of interesting, is because hearing and sound is a little bit weird, what happens when we play these frequencies? What is that experience like? So let's switch over and let's see what it sounds like. So this is that tone generator that I had up last time. Everybody kind of hear that low hum? So I'm going to put it on those frequencies. Again, if this starts to hurt, don't be embarrassed if you want to close your ears because it could feel quite sharp. So let's get around 3,500 first. Okay, I just turned the volume down there. Okay, so there's going around 3,500. Let's get up to 10,000. Okay, maybe you notice something when we hit around there. Might not be as effective because I got the volume turned down, but I don't want to turn it up too high either because I think it's a little painful. Okay, now I'm going to try the last one. This is going to be a you experience, not a me experience, because I can't hear it anymore. Okay, now I'll hit stop. So biologically speaking, if you give people a hearing test, when you hit these sweet spots of frequencies, when you come to these three, people will kind of naturally do this and say it's too loud. People experience those resonant frequencies as being very loud because you're getting the standing waves in the ear canal. So that's kind of an interesting application. Okay, let's do one more example, then I think we'll be ready to move on. So we have a 50 centimeter long tube. So this is the length, 50 centimeters. It's capped at both ends. So this is a tube that's closed at both ends. Kind of the notation is we do C/C. Standing waves are excited in the tubes by tapping one end. We know the speed of the sound in air and speed of sound in helium. So part A says find the frequencies of the first three harmonics in the tube. And just to clarify, we're going to say that the tube is air-filled. Helium gets to be important in part B. So let's find the first three frequencies. So if our tube is closed at both ends, we know that our conditions for standing waves in the tube, Fn, is n times V over 2L, where n is 1, 2, 3, and so on. So we get the full set of harmonics in tubes that are closed at both ends or if they're open at both ends. So those tubes are exactly the same. So our first frequency, F1, our fundamental frequency, is equal to 1 times 344 meters per second, divided by 2 times 0.5 meters, and we get a fundamental frequency of 344 hertz. Okay, nothing earth-shattering there. Our next frequency we would have to find F2. You could either do 2 times V over 2L, or we could do 2 times F1. And we get 688 hertz. And our next higher frequency, we can do 3V over 2L, or 3 times F1, and we get 1,032 hertz. And all of these are in air. Okay, any questions? It's just kind of a plug and chug. Right. Part B, if we take our tube and we fill it up with helium, and this is an experiment we used to do in Physics 1051 till helium got kind of a world scarcity. What would happen to the frequencies? So right off the bat, do you think they'll get bigger or smaller?
Bigger.
Definitely going to get bigger. And the reason we know that, kind of two ways. First is mathematically, the frequency is n times V over 2L. Our speed of sound and frequency is a lot bigger. Like it's kind of handy to 3 times as big. The second might be just a little bit more lifestyle. Anybody do the party trick of sucking in on the helium balloons? And your voice sounds so silly, right? So you know the frequencies get higher because maybe you've experienced that in your life. As a professional, I actually don't recommend that you do that. The stuff in the balloons is not guaranteed clean, so it may not be wise to suck it in. However, you live your choices. So part B, what happens when we put helium in our tube? So we'll just repeat the problem. Part B. Fn equals n times V over 2L. So because V is bigger, Fn will increase. There's a qualitative statement and a reason. Let's see how much they increase by. So our fundamental frequency F1 is 1 times 999 meters per second divided by 2 times 0.5 meters. Gives us a frequency of 999 hertz. So that frequency is bigger as we anticipated. F2 is twice F1 equals 1998 hertz. And F3 is 3F1 equals 2997 hertz. Okay, so those are our frequencies. For homework exercise, you can try and find the wavelengths associated with each of those frequencies and draw those standing waves in the tube. When you're drawing the waves in the tube, you might notice that the question doesn't specify draw the pressure waves or draw the displacement waves. That means you can choose for yourself which set of waves you prefer to draw. Just be sure you label it, that you show did you draw pressure or did you draw displacement. Okay, questions? You still good? So now we have another application of standing waves. I think this is kind of neat. This stuff becomes important when you talk about music. Music is kind of important for just general human appreciation of life. So you can listen to two different stringed instruments, and my picture here is I've got a banjo and a cello. On the surface, they're kind of the same instrument, right? They've got a body, and they've got strings that are attached at two ends. So on the surface, a banjo and a cello are the same thing from one point of view. From the point of view of listening to a banjo versus a cello, they don't sound the same, right? You know, both fantastic, I'm not here to judge, but they don't sound the same. A cello is kind of very rich and very full, but a banjo is not so much that description. Likewise, these two instruments are a recorder and a flute. Did most people play the recorder when you were in grade school? Like it's a very grade 5 sort of thing to do? Yeah, okay. Your parents told you it sounded wonderful. They were not being completely forthright. So a recorder and a flute are kind of the same instruments. They're a tube with holes. You blow in one end to get the sound come out. A recorder is a bit sharp, right? And it doesn't sound the same as a flute or a clarinet, which is much richer and much more full. So why are they different? If they're the same thing, why are they different? That's a good question, right? So we can think about it in terms of all these resonances and stuff. I thought about grabbing my kid's recorder and flute and bring it in, but I can't play it anyway, so I didn't bother in the end. So what I've got here, this is an instrument on my phone. It's called a fast Fourier transform analysis, an FFT device. We know that sound waves are pressure waves in air. So hang on, I've got an oscilloscope too. So when you make a sound, it looks like a sine wave. So this is measuring the pressure of my voice as it hits the microphone, and that's wobbling back and forth, and it's turning it into a wave. Mostly it looks sinusoidal, but we get some glitchy stuff too. If I turn on the FFT, it's showing the frequencies in my voice right now. So two different musical sounds I can make is I could whistle. I'm going to try. I'll leave the mask on at first. No, sorry. Okay, did everybody see what popped up on the FFT? Okay, I am not a great whistler. Yes, this is a little embarrassing, but I will go forward. So the whistle didn't sound that great, and it was a single note, right? There was just one frequency there. If I sing, this is worse than the whistling. La 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 la. Okay, that's marginally better, and there are more frequencies. So music that sounds nice is music that has multiple standing waves. Okay, so things that don't sound so nice probably just have a single frequency. Things that are lovely and rich and full have lots and lots of frequencies present at the same time. So on the cello string, you've got so much happening with a cello. You've got multiple standing waves on the string itself. That transmits into the body of the instrument, which is this lovely shaped instrument with different kinds of wood. that makes standing waves in the cavity of the cello. And all of these waves come together to make that beautiful sound you hear when you hear a cello play. Likewise with the flute and the recorder, their design lend themselves to numbers of standing waves in the device. Something maybe a lot of people have tried at home, shower singing. Got any singers in the shower? Got to be some people. You're just not putting your hands up. I know you do it. Yeah, there we go. The reason people like to sing in the shower is because it sounds terrific, right? You can be a terrible singer in your living room, but as soon as you're in that shower, it's just marvelous. Because you're in this box of air, your sound causes resonances in the standing waves in the air column in your shower, and that's why it sounds so nice. If you wish to try this in public, if you go into the stairwells here in this building, like the smaller stairwells, and if you sing in those, boy, that sounds just as nice as in a shower. So I invite you to brighten somebody's day and sing as you're going up and down the stairs in this building. People will love you for it. Okay, questions? Yeah, and if you like that stuff, I don't know, you might be interested in doing a music course. Maybe they talk more about that in music theory. It sure would be fun to learn about. Okay, now moving on. We're going to come back to interference. Well, I guess we've been talking about it all along, but we're going to look at it now in a new way. Let's say that we have two sources, and they're going to emit sound in phase. Okay, so let's elaborate what we mean by two sources. By two sources, I mean that I have two speakers playing sound. In real life, if I was going to set this up and do it as an experiment, speaker number 2 would be right here. It's emitting a sound wave that's coming out like this. Speaker number 1 is just a little bit in front of speaker number 2. It's emitting a sound wave that comes out like this. And we're going to talk about what people hear when the two sound waves come together. So what does this person hear? So our real setup is that those speakers in a line and the waves are on top of each other. That's going to make our pictures and our diagrams difficult to draw. So just in my picture, I'm going to separate them. But really, it looks like this. Okay. So there's our setup. My question is, a person has her ear at the dash line. So there's a person standing right here listening. In this picture, I'm going to put my person right here. If this person is standing right here, what kind of interference is happening where that person is standing, and what does that mean about what she hears? So if you look at those waves and where they meet where she's standing, what kind of interference do you think that is? Okay, constructive I'm hearing coming from a lot of people. So these waves meet crest to crest. When waves meet crest to crest, we know that's constructive interference. So that means the sound that she's receiving from the two speakers, the sound wave gets bigger. In terms of actual sound, that means it gets louder, right? When we put lots of sound together, it gets loud. So our person hears loud sound. So our assumption was at the beginning, our sound waves are emitted in phase. To make sure we all understand what this means, is when the sound comes out of the speaker, it's coming out the same way from both speakers. So both speakers might be emitting sound at a crest, or both might be on a trough, but whichever it is, it's exactly the same. That's what in phase means. So in phase, we'll say, example, both emit on a crest. We're going to talk about sources that are either in phase or out of phase. So in phase is exactly the same way. When we get to out of phase, it will be exactly the opposite way. If you wonder, could it be somewhere in between? The answer to that question is yes, but we're going to stick with in phase or out of phase for our analysis. Okay, so there's our setup, our in phase, and our person hears constructive or loud sound because the waves meet crest to crest. So there's kind of a qualitative look. Let's do a mathematical analysis and see if we can figure out a method for deciding if a person's going to hear constructive or destructive. So let's make a couple of definitions. Our first definition is we're going to define the distance D1 as the distance between the person and speaker 1. So I'm going to label my speakers 1 and 2. Oh, they're already labeled for me. Speaker 1, speaker 2. So my distance between my person and speaker 1 is D1. And you might think it's silly, but it has been my experience that with this section of the course, this little bit we're going to do now, the biggest problem students have is with this definition and the next two I write down. People have trouble remembering these. So please make yourself not one of those people. If you can remember these definitions, you're probably going to get full marks on your questions when you do it on the test. Our next definition is going to be D2. This one probably isn't going to surprise you, person to speaker 2. As you do these problems, you should always be drawing D1 and D2, because pretty often you're going to have to figure them out from the geometry of the problem. So D1 and D2 is from the person to the speaker. Then delta D is what we call path difference. And delta D is the difference in the two paths, right? How much bigger is one than the other? So we say it's the absolute value of D2 minus D1. We use absolute value because we don't care which one is bigger. We just want to know how much they're different by. Okay, so how different are they? So it's really important to keep these definitions straight. If you can keep those straight, you're going to do great in all these problems. So in our problem, D2 is from here to here. D1 is from here to here. So D2 take away D1 gives this much left over. Okay. So we have D2 is from here to here. We take away D1 and we're left with this much. So there's our path difference in this picture, delta D. If we're trying to figure out what people are going to hear, we care about sound, we care about frequency and wavelength. Let's try and relate delta D to the wavelength in the picture. So if I trace a line up from here, I see that that's where this speaker is. If I trace a line down from here, I'm going to trace over my wave right here. How much of a wavelength is this? That's a full wavelength right there. So in this picture, delta D is equal to a wavelength, and our person hears loud sound. So delta D equals lambda, and the result is constructive interference or loud sound. So far, so good? You good with the definitions, the setup, lambda? All right, super. So this isn't the only setup we can have, of course. I'm going to take my speaker 1, and I'm going to move it down a little bit. Let's kind of go through this idea again and see what we get when we move speaker 1. So I've moved speaker 1, and I want to know what kind of interference does our person hear here? Does our person hear? So where this person is, my waves are still meeting crest to crest. Crest to crest means constructive interference. In terms of sound, that means a loud sound. Okay, so to answer our question, the waves meet crest to crest, which means constructive interference, which means loud sound. Okay, in terms of D1, D2, delta D, and lambda, let's have a look at that. So D1 is from the person to speaker 1. D1 is pretty small this time. D2 is my person to speaker 2. D2 hasn't changed. Delta D is what's left over when I do D1 minus D2. So this is my delta D. If I look at my wavelengths, and this time my delta D goes from here to here, and then from there to there. So in my delta D now, can split this into 2 bits if you like. This distance is 1 full cycle lambda. This distance is 1 full cycle lambda. So this time, when I shifted my d down, I made my delta d equal to twice the wavelength, and I'm still getting constructive interference or loud sound. So in this situation, delta d, my path difference, which is d2 minus d1, is equal to 2 lambda when I get my constructive or loud. So a general conclusion, and I could keep going with this all day. I could move 1 back and forth or move it ahead. I would find that every time my delta d was an integer multiple of the wavelength, I would find that I had constructive interference. Okay? So whenever you move it by a full wavelength, those waves are going to meet crest to crest and we're going to get constructive. So our general conclusion is if 2 sources emit sound in phase, we get constructive interference or loud sound whenever we have the condition delta d equals d2 minus d1 equals n times lambda, where n is our integers 0, 1, 2, 3, and so on. Okay? So whenever you have this for your path difference and your sources are in phase, you will get loud sound. Still good? Okay, so that was when we moved it by a full wavelength. We don't have to move it only by wavelengths. Let's move speaker 1, but a different distance. So I've got my 2 sources emitting waves in phase. I'm trying to be really specific about that this time. I've shifted speaker 1, and I'm asking in this setup, now what kind of interference do we have? Destructive. Why is it destructive? Okay, I think I'm hearing all the right things. So the wave from speaker 2 gets to the person at a crest. From speaker 1, it gets to a trough. So the waves are meeting crest to trough. When waves meet crest to trough, they cancel out. That's our perfect destructive interference. In an ideal world, the person would not hear any sound at all. It would be a perfect cancellation. Our world is a little bit more real than that. So instead of saying silence, I'm going to say quiet. So it's going to be quiet sound. It won't be loud. So it'll mostly cancel, but there'll be some reflections from the room around you. You'll hear a little bit. So let's apply our method here. D1 is from my speaker 1 to the person. So there's D1. D2 is my person to speaker 2. Delta D is what's left over when you subtract them. So let's show that on the picture. So here's my delta D this time. What fraction of a wavelength do I have here? There's a half of a wavelength in that picture right here. So when my waves start in the same way, if the path difference is off by a half of a wavelength, we're going to get destructive interference. So I've got delta D equals D2 minus D1 equals lambda over 2, giving me destructive interference. If I move this down a full wavelength, I would find that I would still get destructive. So it's also true if delta D were 3 lambda over 2, or 5 lambda over 2, or so on. So basically, whenever they're off by a half wavelength, so a something 0.5, that's when the waves are going to meet crest to trough. That's when you're going to get your destructive. So if they're off by a full wavelength, it's constructive. Half wavelength, it's destructive, if they're in phase. So then our general conclusion, we've got our sound sources in phase. We get destructive interference when delta D, which is D2 minus D1, can't forget that bit, equals n lambda over 2, where n is 1, 3, 5, Some books, if you're not using the course textbook, you might see a different equation right here. You might see n plus a half times lambda over 2, plus a half times lambda. If your equation is a little different, that's fine. Just make sure you show it clearly. You can get the same result if you have a different n value. This is what your book uses, so this is the one I'm going to stick with. Feel good? Okay, so that's constructive and destructive, loud and quiet when our waves are in phase. Now let's talk about out of phase. So what happens if our two sound sources emit waves out of phase? So that means one might, so for example, one on crest, other on trough. So how do we get our constructive and destructive if they're out of phase, if they're emitting in opposite ways? So let's go to the same idea. Let's put our person right here. Let's put our speaker set up like this, and let's ask, what is our friend here? So the friend is here. The sound from speaker 2 is at a crest. Speaker 1 is at a crest. The waves are meeting crest to crest. That's constructive interference. The person hears loud sound. Okay. So what our person hears is because the waves meet crest to crest, we've got constructive interference, which means we get loud sound. Let's look at our D1 and our D2. D1 is from the person to speaker 1. D2 is from the person to speaker 2. Delta D is the difference between those two. So our delta D is from here to here. So this time, when our sound sources start in opposite ways, we get constructive interference if delta D is a half wavelength. Okay, so in this picture, our delta D is a half wavelength. So if they start out of phase, you've got to shift it by a half a wavelength, essentially to get them back in phase. Okay, so when you shift by a half wavelength, you're going to get your constructive interference. So if we're out of phase, we get constructive interference when delta D, which is D2, take away D1, equals n times lambda over 2, where n is your odd integers. Okay, and I've got a slide where I've got this typed up nice and neat, everything on the same page. But we're going to do one more like this, and we're going to talk about out of phase with destructive and get the condition for that one. So here's our last one. We've got our sources out of phase. What does our person hear? So the person is here. The sound from speaker 2 is at a crest. Speaker 1 is at a trough. Sound waves are meeting crest to trough. That means those waves are going to add up to be 0. That's destructive interference, which will correspond to quiet sound. Let's look at our D1 and our D2 and our delta D. So we label D1, we label D2. Delta D is the difference between those two things. When we look at our wavelength compared to our delta D, we see that delta D is a full wavelength. So delta D equals D2 minus D1 equals lambda. So in this picture, the waves start out of phase, we shift it by a full wavelength, they stay out of phase, we get destructive interference. So our general conclusion is that if our two sources are out of phase, we'll get destructive interference whenever the path difference delta D, which is D2 minus D1, equals n times lambda, where n is our integers, including 0. Okay, so we went through the setup for each of them. Now let's just put it up on a slide all by itself. Wait till people are done with this. Okay. So here's our summary. I'm going to post this. You don't have to write it all down if you don't want to. So we get our constructive interference when waves meet crest to trough. We get our destructive, We get constructive interference when waves meet crest to crest, or trough to trough in the same point. We get destructive when waves meet crest to crest. If our waves start initially in phase, we get constructive as delta D is n lambda, destructive if it's n lambda over 2. If our waves are out of phase, those conditions flip. That's how a lot of people just tend to remember it, which is fine if you remember it that way, but it's good to remember this start point, which is where it comes from. So here's a slide you can use for a reference if you're going back and you're trying to answer your questions and you just want to have that all written out nicely for you. So let's talk about an application. We still got 5 minutes left. We can do a little bit more. So one application, maybe this is something a lot of people have, but not everybody. Am I out of line if I assume everybody has headphones or earbuds? Of everybody who has headphones and earbuds, how many people have noise canceling ones? Oh, lots of people. I don't blame you one bit. The world can be a very loud place. So I brought in mine. I use these a lot because they have really good sound and it kind of tunes out a lot of the things I have in my life. This explains how those work. So when you put on your headphones, your noise canceling headphones, somewhere on the outside of your headphones, there's a little mic pack. It's not very big, it's just a small microphone, just like your mic on your cell phone and your laptop is really small. That mic picks up all the ambient noise around you. It's recording the sound that's outside you. It records it as a sound wave, just like my phone was doing when I was speaking and it was showing the wave. It records that sound wave, turns it into a digital signal, and then it turns it 80 degrees out of phase. It turns it upside down, it flips it. It plays that sound back to you. So it takes the sound from outside, makes it out of phase, plays it back, and it cancels the two sound waves. That's why you don't hear anything, because those sound waves are canceling at your ears. So if you ever wondered how they worked, that's it. So it's not a physical blocking of sound for most of them. It's an electronic thing of playing the sound waves back. Let's try our last problem. It's really quick, and I'm going to hope we can get through it. Okay, so here's you. You're standing in between two speakers. They're playing a tone in phase of 172 hertz. So this is the frequency. Assume the speed of sound in air is 344 meters per second. There's our V. And here's you and your two speakers. So part A, what is the wavelength of the sound? That one's super straightforward. So part A, V equals F times lambda. It means lambda is equal to V over F, 344 meters per second, divided by 172 hertz, equals 2 meters. Okay, so there's part A, pretty straightforward. Part B, and this is leading you to water here. This is trying to take you through the process of how to get to your solution. In a test problem, I might not give all of these initial steps. I might jump to a final question, so you'd have to know you needed to do these steps. So part B, what is the path difference? Let's write down that delta D is D2 minus D1. As soon as you write that down, you have to show D1 and D2 on your picture. So I'm going to call this speaker on the left speaker 1. That makes this D1. I'm going to call my speaker, left and right. My speaker on the right is speaker 1, speaker on the left is speaker 2. So my person to speaker 2 is D2. Let's see if I can figure out what D1 and D2 are. D1 is easy. D1 equals 4 meters. D2 is a little bit more difficult. I see D2 plus D1 equals 12 meters. So D2 is 12 meters minus D1, which was 4 meters. So D2 is 8 meters. Okay, clearly I was overly optimistic and we're not going to finish. So we'll quit there. Today is my day. I've got to run to another class, so I can't hang around for questions, but I'll be in all afternoon if you want to drop by or send me an email.